So I want you to imagine trying to send like an urgent, super complex, and highly confidential message across an entire continent.
Okay, that sounds stressful already.
Right. But here's the catch. You are completely stripped of the modern digital grid.
Oh, wow.
Yeah, so no wires, no fiber optics, no batteries, no microchips, absolutely no satellites, and definitely no smartphones.
That is a profound constraint to place on ourselves.
How would you actually go about conquering that massive expanse of geography?
It's fascinating because, we are so accustomed to the friction of distance being essentially zero today.
Probably. We don't even think about it.
Right. We take it completely for granted that information just moves at the speed of light right in our pocket.
Yeah, you just hit send and it's there.
Exactly. But for the vast majority of human history, that exact scenario wasn't just some fun hypothetical thought experiment.
It was literally everyday life.
It was the daily, inescapable reality. Think about empire building, or managing global trade, or just simple human connection.
You had to solve that geographic puzzle just to survive.
Precisely. If you want to run a country, you had to beat the distance.
And that puzzle is basically our entire focus today. So welcome to this deep dive into the world of early long-distance optical signaling.
It is such a great topic.
We're looking at how humanity managed to conquer distance long before the digital age, mostly using, fire, smoke, and some genuinely massive mechanical arms.
We really do have an incredibly rich foundation for this exploration today.
Yeah, the source material is amazing.
It really is. We're looking closely at this era of communication that predates electricity entirely. And, while this era might seem completely ancient, the core architecture of how we communicate today was basically forged right here.
Which is wild to think about.
It is. We're going to connect the dots between, like, a bonfire on a distant hilltop and the digital data routing that powers whatever device you are using to listen to us right now.
Exactly. And our mission today is to extract those structural and logical blueprints. Because when you really look at these early visual networks, they weren't just primitive stopgaps, right?
No, not at all.
They weren't just these historical novelties holding us over until the iPhone showed up.
Right. They were serious infrastructure.
Yeah. Okay, let's unpack this. They actually laid the foundational logic for the modern internet.
They absolutely did.
So whether you're a networking engineer or a history buff, or you're just someone who is insanely curious about how the world works, this deep dive is going to give you a whole new perspective on what it means to actually send a message.
I think we need to start by looking at the fundamental why behind all these systems.
Like, why build them in the first place?
Yeah, exactly. Why did we need to build towers and light fires?
Right.
To understand that, you really have to understand the absolute baseline of human communication, which was violently limited by our immediate physical environment.
Because we were stuck on the ground.
Completely stuck. Before we started looking up to the sky to send signals, we were trapped relying purely on acoustics.
Right. Primal audible signals. Like our first real attempt at networking was just yelling really loudly at each other.
Pretty much. And, well, when that didn't work, we got creative.
Which makes sense. We developed indigenous whistle languages designed specifically to carry across deep valleys.
Because a high-pitched whistle cuts through ambient noise way better than a shout ever could.
Oh, for sure. But out of all those acoustic methods, the most sophisticated ones were definitely the talking drums of West and Central Africa.
The talking drums are just a brilliant piece of engineering, and they operate on a principle that is entirely different from how most people today probably imagine them.
Yeah, I think people misunderstand them.
They do. Because when we think of drum communication in the West, we often default to something like Morse code.
Right, like a binary system.
Yeah.
Just short and long taps that represent individual letters.
Exactly.
You picture a guy just banging out a rhythm that literally spells out, danger is coming.
Right. But that is not what these were doing at all. These drums were not spelling words out letter by letter.
So what were they doing?
They were mimicking the spoken language itself.
Wait, really? Mimicking it?
Yeah. Many languages in West and Central Africa, like the K language, for example, are tonal languages.
Oh, okay. So the pitch matters.
Exactly. That means the pitch of a spoken syllable fundamentally changes the meaning of the word itself.
So if you say a word with a high pitch, it might mean one thing.
Yep. And if you say the exact same syllable with a low pitch, it means something completely different.
Ah, okay. So the drums were basically built to replicate those specific pitches.
That's it, exactly.
That makes so much sense.
Yeah.
I mean, they're usually carved from a single hollowed-out log with a slit in the top, right?
That is the traditional design, yes.
And the wood is carved to, like, different thicknesses on either side of the slit, so you get two distinct tones, like a high tone on one side and a low tone on the other.
That is the precise mechanical setup. So by striking the different sides of the drum, a really skilled drummer could actually replicate the tonal contours of an entire spoken sentence.
That is just wild.
They were essentially creating a completely surrogate language.
Wow.
They could transmit incredibly nuanced news, like the birth of a child, the arrival of strangers, or even the outbreak of disease, all across these vast distances.
It's almost like an ancient form of frequency modulation.
Oh, that's a great way to put it.
Because, I mean, if the meaning of the word relies on the pitch shifting up and down, the drummer's basically modulating the frequency of the sound waves to encode complex data.
Right.
It's sort of like how an FM radio wave carries an audio signal today.
That is a phenomenal analogy, really. They were actively modulating the acoustic frequency to carry a high-density data payload.
And they were loud, right? Like, these were not small drums.
Oh, they were massive. Because they were so large, the sound could travel several miles through the jungle.
So a neighboring village would just hear it, decode it, and pass it on.
Exactly. Their drummer would hear it, translate the tones, and then relay it on their own drum to the next village down the line.
So complex news is just leaving from village to village.
In this way, detailed information could travel at speeds that utterly humiliated a human runner.
I bet. But, okay, if these drum networks were so incredibly sophisticated and they could literally broadcast the spoken word across the jungle, why did we ever abandon them?
That's the big question.
Yeah, like, why isn't there a global network of talking drums today?
Well, unfortunately, it comes down to the unforgiving physics of sound and the limits of our atmosphere.
The air just gets in the way.
It does. Acoustic energy dissipates incredibly fast. Sound waves are, by their nature, very fragile.
Right?
They get absorbed by thick vegetation, they get deflected by mountains, and they are easily scattered by wind and rain.
So if a massive thunderstorm just rolls in, your entire communication network just goes completely dead.
Totally offline, the signal just gets drowned out by the thunder and the rain.
Yeah, that makes sense.
And even in perfect weather, to send a message over a truly continental distance using sound, you would need an absurdly dense network of relay stations.
Like, how dense are we talking?
You would literally need a drummer every few miles, spanning thousands and thousands of miles.
Oh, man, the logistics of that.
The sheer manpower and coordination make it impossible to scale globally. The physical medium of the air itself basically caps your range.
You literally just hit a wall.
You do.
So if you can't shout it and you can't drum it because the atmosphere just eats the signal, what do? You are forced into the next phase, which is physical carriers.
Exactly.
If the information can't travel on sound waves, you have to physically carry the information yourself.
And this is a crucial threshold in the history of information. For thousands of years, we were stuck with this inescapable bond between information and physical mass.
Right, they were tied together.
Yes. To move a thought, you had to physically move an object. The data was inextricably tied to a physical substrate.
Whether that substrate is like a heavy Mesopotamian clay tablet or a scroll of Egyptian papyrus or literally just the brain of a guy running as fast as he can.
Exactly.
When you look at the historical record, it's actually wild how much we relied on sheer human endurance.
It really is.
You have the Aztec Pinani, right? Those elite relay runners who basically kept the empire connected.
A phenomenal system of human relays, yeah.
And then you have the legendary Greek runner at Marathon. But the problem is, humans get tired.
Humans get very tired, and horses need water.
Right?
Both are fundamentally limited by their own biological mechanics. You can only move mass across the surface of the Earth so fast.
There's a hard speed limit.
A very hard one. This is why we eventually turned to the sky. Not with optical signals yet, but with biological ones.
Oh, you mean animal couriers?
Yes. Homing pigeons became the ultimate high-speed data transfer mechanism of the ancient and medieval world.
Ah, the pigeon network. It wasn't just ancient Egypt, Greece, and Rome using them either.
No, they were used everywhere.
The Rothschild financial dynasty famously used pigeons, right?
They did.
They used them to get advanced word on the outcome of the Battle of Waterloo so they could dominate the London Stock Exchange.
It was essentially high-frequency trading in the 19th century.
That is hilarious.
Yeah.
And even the early Reuters news service used a huge fleet of pigeons to bridge a gap in the telegraph lines between Germany and Belgium.
Humming pigeons were just a brilliant optimization of the physical transport layer.
Because they just fly over everything.
Exactly. They provided an unparalleled direct flight path that could completely ignore terrestrial obstacles like mountains, wide rivers, and enemy armies.
So they were functionally like a biological airborne data packet.
That is exactly what they were.
But, I mean, the vulnerabilities are almost comical when you think about them by modern standards.
Oh, the failure rates could be quite high.
Right, because a pigeon is just a one-way journey. You send it back to its home loft, but you can't, like, program a pigeon with a new destination address.
No, you definitely cannot.
You can't just say, hey, bird, fly over to Paris and drop this off today. They only know how to go to one place.
Home. Right, the routing was strictly hard-coded.
And on top of that, your literal data packet can get eaten by a hawk.
That was a very real problem. Hawks were the original packet loss.
It can get blown miles off course in a bad storm. And your bandwidth, like your actual payload capacity, is literally just whatever tiny scroll of paper you can tie to a bird's leg without grounding it.
And this brings us right back to your earlier point about the sheer physical constraints of moving mass.
Yeah.
Using a pigeon or a horse or a human runner to send a message is fundamentally relying on physical transportation to move data.
It's basically the ancient equivalent of the sneaker net.
The sneaker net.
Yeah, you know, when your Wi-Fi goes down and the video file you want to send is way too big to email over a cellular connection.
Oh, I see.
So you just copy it onto a USB thumb drive, put on your sneakers, get in your car, and drive it across town to your friend's house.
Right, you're using physical transport.
You're moving the data physically because the network is broken. But for thousands of years, the sneaker net wasn't just a backup plan when the internet went down. It was the only plan.
It was the absolute only plan, and it introduced massive latency into the global geopolitical system.
Massive delays.
Exactly. The speed of information was strictly limited by the biological speed of whatever carrier was fighting gravity and friction that day.
And that latency must have caused absolute chaos.
Oh, without a doubt.
I mean, think about a huge empire trying to manage its borders. The emperor in Rome makes a major strategic decision based on a report that took, 3 weeks to arrive on horseback?
Easily 3 weeks.
And by the time he sends his new orders back, which takes another 3 weeks, the situation on the ground is completely changed.
The data is incredibly stale by the time it arrives.
Battles were undoubtedly fought, and thousands of people probably died days or even weeks after peace treaties were actually signed. All just because the guy on the horse hadn't arrived yet.
That is the defining tragedy of that entire era's communication limitation.
It's just tragic.
Entire economies and empires were artificially throttled by this. To truly evolve, humanity had to figure out a way to completely decouple information from physical mass.
We had to leave the atoms behind.
Exactly. We had to stop moving atoms and start moving light. We had to figure out how to beat the horse.
Which means we finally start looking up.
Yes, finally.
This is where we transition into the true birth of the optical network. If you want to beat the horse, you harness the speed of light. And the most primal way to do that is obviously with fire.
Fire and smoke genuinely represent the structural genesis of the telecommunications network as we know it.
They were the first real nodes.
Yes. And we have to remember, these weren't just random fires lit by campers. They were highly organized early warning systems spanning entire continents.
You see this globally, right? I mean, the Roman military built massive, complex chains of fire beacons just to coordinate troop deployments across Europe.
They were incredibly organized.
And ancient Chinese garrisons did the exact same thing along the Great Wall.
A classic example.
If the Mongols attacked, they lit a fire, the next tower saw it, they lit theirs, and the message just raced to the capital at the speed of sight.
Let's actually analyze the mechanics of these systems because it's fascinating, starting with smoke signals during the day.
Okay, let's get into the smoke.
Because the way Native American Plains tribes utilize smoke is far more sophisticated than the sort of Hollywood caricature of a guy just waving a blanket over a campfire.
Right, they weren't just lighting a smoky fire and casually letting it billow into the sky for everyone to see.
No, not at all. They were actively manipulating the physics of the smoke itself.
How so?
They would build a very specific fire, often adding green wood or damp leaves, specifically to generate incredibly dense, bright white smoke.
Oh, so it would contrast against the sky.
Exactly. And then they would use a damp blanket to rapidly cover and uncover the fire.
Okay, so by doing that, they're essentially taking a continuous physical process, like a constantly burning fire, and chopping it up into measurable, distinct units.
Precisely. They are creating discrete puffs of smoke. They were taking a continuous variable and encoding it into a discrete variable code right there against the sky.
That's brilliant.
A certain number of puffs, or puffs held for a specific duration, carried specific pre-agreed meanings.
So it wasn't just random puffs.
No, it was a language. One puff might simply mean attention. 2 puffs might mean all is well, camp is safe. 3 rapid puffs might mean danger, enemy approaching.
It's like they were creating ancient data packets out of carbon and hot air.
They absolutely were.
They were actively modulating the visual signal. But even with that incredible level of control, you still run into a massive limitation, right?
You do?
It's the exact same problem with the Roman fire beacons at night. They're incredibly fast, but the vocabulary is almost non-existent.
The bandwidth is just severely constrained. A fire beacon is essentially a 1-bit system.
Right, just a 1 or a 0.
It is binary in the most primal absolute sense. The fire is either unlit, which communicates a status of 0, meaning status quo, nothing to report.
Everything's fine.
Right. Or the fire is actively lit, shifting the status to a 1, meaning danger, invasion, mobilize immediately.
You can't use a single bonfire to transmit a complex narrative.
No, you really can't.
Like if I'm a Roman garrison commander sitting on the edge of the empire, I can't light a fire that says, hey, the enemy is approaching from the north with 500 cavalry and 200 archers. Please send reinforcements to flank them by Tuesday.
No, that level of detail is impossible.
I can literally only light a fire that just screams, enemy.
And that profound lack of granularity was a massive strategic weakness for these empires.
I can imagine.
You could alert the capital that something was wrong, sure, but you couldn't tell them what to prepare for. Do they send an army or just a diplomat?
Exact. You have no idea.
This specific bandwidth problem remained largely unsolved until an ancient Greek historian named Polybius, who was living around the 2nd century BCE, conceptualized a way to dramatically increase the data payload of a visual signal.
Okay, here is where things start getting conceptually brilliant.
It is a huge leap.
Polybius didn't just want to send a 1-bit alarm. He wanted to be able to send dynamic alphabetical text. He wanted to literally spell things out across the mountains.
He was very ambitious.
But how did he actually achieve that using literally nothing but fire?
He developed an encoding system that relied on pairs of torches and a strict geometric grid. We actually still call it the Polybius square today.
Okay, a square. Walk me through it.
Imagine a 5x5 grid drawn out on a piece of parchment. The Greek alphabet has 24 letters, right?
Right.
So you mathematically map each individual letter to a specific intersection of a row and a column on that grid. You just combine the last 2 letters into one square to make it fit exactly 25 spots.
Got it. So you have a grid, numbers 1 through 5 down the side for the rows, and 1 through 5 across the top for the columns.
Exactly. Now, to actually send a message, you build 2 low stone walls on top of a prominent hill with a trained operator standing behind each wall.
Okay, 2 walls, 2 guys.
The operator on the left wall entirely controls the rows. The operator on the right wall entirely controls the columns.
Let's do a little thought experiment here just to see how this actually works in practice.
Sure.
Say I'm the operator on the left, and I want to send the letter B.
Okay.
I look at my master grid. I see that B is located in the first row, second column.
Correct.
So on my left wall, I raise 1 single flaming torch to signal row 1. And the guy on the right wall raises 2 torches simultaneously to signal column 2.
And the receiver, standing on a distant mountain maybe 5 miles away, looking through the darkness, simply counts the torches.
They just count the flames.
Right. They see 1 flame on the left, 2 flames on the right, row 1, column 2. They check their own identical master grid, find that coordinate, and write down the letter B.
Polybius basically invented an ancient pixel,
He really did.
or like a coordinate system. Row 1, column 2 equals a specific, distinct data point. It's literally like playing the board game Battleship, but you are playing it with flaming torches on top of a mountain at midnight.
Philosophically, this was a monumental leap forward. Polybius shifted human communication from sending a localized single meaning signal to creating a universal abstract encoding system.
It's abstraction.
Yes. The torches themselves no longer held any inherent meaning. They didn't intrinsically mean fire or danger anymore.
Right, they're just numbers now.
Exactly. They were just abstract representations of numerical coordinates that mapped to a pre-agreed upon cryptographic table.
I absolutely love the theoretical elegance of that. It is literally the direct ancestor of modern binary code.
It absolutely is the ancestor.
But let's bring this down to messy reality for a second. Let's think about the actual user experience of the Polybius square.
It wasn't great.
I'm imagining trying to spell out an entire tactical sentence, torch by torch, across a windy mountain range.
It sounds exhausting.
It sounds awful. You have a guy picking up 3 heavy burning torches, trying to hold them perfectly steady above a wall. The other guy is fumbling, trying to hold up 4 torches.
In the dark!
In the freezing cold. The wind is blowing the flames all around, probably burning their hands, and the poor guy on the other mountain is just squinting into the abyss, desperately trying to count them before his eyes start watering. That sounds like an absolute logistical nightmare.
It was a nightmare. The operational friction of the Polybius system was its fatal flaw in the real world.
It had to be slow.
It was excruciatingly slow. Think about the physical labor of raising and lowering heavy clusters of torches for every single letter of a long message.
Yeah, your arms would fall off.
And beyond the speed, the error rate was inherently catastrophic.
Because if a strong gust of wind blows out one of my 3 torches on the left wall, the receiver suddenly thinks I'm signaling row 2 instead of row 3.
Exactly. The coordinate changes completely.
An entire letter is corrupted.
Yeah.
And if you're trying to spell out a strategic location, one corrupted letter could send an entire army to the wrong city.
Precisely. The synchronization required perfect timing and perfect visibility. If the operators didn't lift their torches at the exact same fraction of a second, the receiver might miscount the total number of flames.
It's just too delicate.
It required a level of meticulous robotic transcription that humans are notoriously bad at, especially in the middle of a freezing night under the extreme threat of war.
So while fire was incredible for that single adrenaline-pumping binary alert, like lighting the beacons of Gondor and Lord of the Rings to call for aid, it fundamentally failed at complex, nuanced communication.
Fire is just too volatile a medium.
It flickers, it blows out, it changes shape constantly. If you want to encode complex data visually, you need a medium that is stable, distinct, and crucially, works during the daylight.
Which forces a completely different geographical environment to take the lead in communication technology for a while.
Right, because the mountains were too hard.
The rugged, mountainous terrain of Europe was just too difficult to conquer with complex visual signals at first. So the real breakthrough happened out on the water.
We moved from the mountains to the oceans. Naval flags, and the desperate need for nuance.
Yes.
Why did flag signaling become the absolute gold standard for maritime communication?
Well, consider the geography of the ocean itself. It is a completely flat, unobstructed plain.
Just flat water everywhere.
Right. The horizon provides an absolutely pristine line-of-sight environment. There are no mountains in the way, no forests, and no cities blocking your view.
It's the perfect canvas.
Exactly. And furthermore, a naval fleet operating out on the open water is in a unique state of total isolation.
Because you can't exactly ask a messenger on a horse to sprint across the Atlantic Ocean with a scroll to tell the ship next to you to turn left.
No, you certainly cannot. And naval warfare in the 18th and 19th centuries was becoming incredibly complex.
The ships were getting bigger, the fleets were larger.
You had fleets of dozens of massive, heavily armed warships that needed to coordinate dynamic, incredibly precise maneuvers.
Like a giant ballet with cannons.
Exactly. If an admiral wanted the entire fleet to suddenly form a line of battle or flank an enemy's rear guard, they needed a way to broadcast that command instantly to every single captain simultaneously.
The British Royal Navy really pioneered this.
They were absolute masters of it.
The system used by Lord Nelson during the Napoleonic Wars, everyone knows the famous signal at the Battle of Trafalgar, where he signaled, "England expects that every man will do his duty."
A legendary moment in naval history.
He sent that entire message entirely, with flags hoisted up the mast of his flagship, the HMS Victory. But how did this flying system actually elevate the game compared to the slow, clunky Polybius torches?
It fundamentally shifted the entire concept of encoding. They moved away from spelling individual letters like Polybius did to using a macro vocabulary of signals.
Ah, okay, so it's not letter by letter.
No, unlike a beacon fire, which is a single hard-coded message, or the Polybius square, which forces you to painstakingly build words letter by letter, flag combinations allowed for dynamic, modular, macro-level communication.
So instead of hoisting a flag for A, pulling it down, then hoisting a flag for T, then another flag for T, then ACK, you were doing something much more efficient.
Vastly more efficient. They developed a massive expansion of bandwidth by utilizing color geometric patterns, and vertical placement on the halyard.
They really used the visual
They
space.
did. You had square flags, triangular pennants, flags with bold stripes, checkers, and crosses. And the absolute key to all of this was the codebook.
The codebook.
Yes, every single captain in the fleet had an identical, heavily guarded codebook.
So if Nelson hoists, let's say, a red flag with a white cross, and he puts it over a blue and yellow checkered flag, the captains on the other ships just look through their spy glasses, identify those specific flags, flip open their codebook, and find that exact combination.
That's exactly how it worked.
And that combination might translate to an entire complex sentence, like tack to starboard and engage the enemy's rear guard.
You've hit on the exact mechanism. This system eventually evolved into the International Code of Signals that commercial shipping literally still uses today.
That's amazing.
You weren't transmitting letters anymore. You were transmitting whole ideas and complex commands in a highly, highly compressed format.
It's basically the maritime equivalent of sending a pre-programmed emoji or a quick reply text on your smartphone.
An emoji.
Yeah, like instead of typing out, "I am currently laughing out loud at the joke you just told me," which takes forever, you just send the crying laughing face emoji.
Oh, I see.
It packs a massive amount of complex meaning and emotion into a single instant visual burst.
That is actually a perfect parallel. The flag hoist was a standardized data macro. It dramatically reduced the latency of command and control on the water.
It sped everything up.
It did. But as revolutionary and elegant as flags were on the flat, breezy expanse of the open water, they hit a brick wall when humanity tried to adapt them for terrestrial use.
Right, because Europe is not a flat ocean.
No, it is not.
It is full of trees, hills, sweeping valleys, and uneven terrain. If you stick a flagpole down in a valley in France and run up a blue and yellow checkered flag, no one 30 miles away is going to be able to see those colors through the atmospheric haze.
Exactly. The atmosphere ruins the contrast.
Let alone distinguish the pattern. The medium of cloth just isn't bold enough or rigid enough for the land.
The contrast is far too low, and the environment is entirely too cluttered. To conquer the landmass at the speed of sight, flags simply wouldn't cut it.
They needed something bigger.
Humanity needed a revolutionary physical architecture. The communication medium had to evolve from a piece of cloth flapping on a mast to a dedicated, rigid industrial-scale infrastructure.
And that necessity brings us to the absolute centerpiece of this entire evolution. The system that essentially functioned as a mechanical internet.
Yes.
The Chappe telegraph.
Calling it a mechanical internet is really not an exaggeration at all. The Chappe telegraph, which was invented by Claude Chappe in France during the 1790s, was an absolute marvel.
It really was.
It was a marvel of engineering, of cryptography, and perhaps most importantly, of administrative organization.
We really have to set the historical scene here to understand the pressure cooker that forged this invention.
The context is everything here.
It's the early 1790s. The French Revolution is in full swing, the monarchy has completely fallen, the Republic is born, and almost immediately, France is surrounded and invaded by a massive coalition of hostile European powers.
Britain, Austria, Prussia, they were coming from all sides.
Right. They were fighting a desperate multi-front war for survival. Paris, which is the nerve center of the whole country, is completely isolated from the front lines.
The young French Republic was facing a true existential crisis.
They were terrified.
The central government in Paris needed to know what was happening on the borders instantly, and they needed to send military commands back just as fast to coordinate their armies.
But they only had horses.
Exactly. The speed of a horse courier meant that Paris was always days behind the actual reality of the war.
So they were making decisions based on old news.
Always. Claude Chappe recognized that whoever could communicate fastest would inherently win the war. So, he approached the National Convention with a wild proposal to build a nationwide optical network.
Okay, I have seen diagrams of these Chappe towers, and they look incredibly strange, like really weird.
They are very unique looking.
For someone listening who has never seen one, describe what this massive machine actually looked like.
Picture the beautiful French countryside. Now, every 6 to 10 miles, built on the highest natural elevation they could find, or sometimes right on the roofs of existing buildings or churches, is a sturdy stone tower.
Okay, a tower every few miles.
Emerging from the roof of that tower is a massive central wooden mast, perhaps 30 feet tall.
That's huge.
It is. Attached to the very top of that mast is a large pivoting wooden beam called the regulator. That beam is about 14 feet long.
Okay, a big beam on a mast.
And attached to both ends of that 14-foot regulator are two smaller articulated arms called the indicators.
So if you were looking at it from a distance, it almost looks like a giant, rigid wooden stick figure standing on top of a building, waving its arms in these highly specific geometric poses.
Visually, it was quite striking, a bit like a giant mechanical scarecrow, but mechanically, it was an instrument of intense precision.
It wasn't just flapping around in the wind.
No, not at all. The operator wasn't up on the roof wrestling with these heavy beams. They were stationed safely inside the operating room at the tower base.
Well, they were inside.
Yes, using a highly complex system of heavy counterweights, brass gears, thick ropes, and pulleys, the operator could manipulate those massive wooden arms into a wide variety of specific, rigid angles against the sky.
And the angles are what matter, right? Because it's not just waving them around randomly. Each specific configuration of the regulator and the indicators represented a different symbol, a number, or a control code.
Exactly. The regulator, that main large beam, could be set to 4 distinct angles: perfectly horizontal, perfectly vertical, or tilted exactly 45 degrees to the left or right.
Okay, 4 positions for the main beam.
And the smaller indicator arms at the ends could each be set to 7 different precise angles.
Wow.
When you mathematically multiply the possible combinations of the regulator and the 2 indicators, the machine was capable of displaying 196 distinct shapes.
196 distinct data points.
Yeah.
That is a massive, massive leap in vocabulary compared to the Polybius square.
It's an astronomical leap in bandwidth.
And the speed is what truly blows my mind about this system. The first fully operational line connected Paris to the frontline city of Lille in 1794. It's a distance of about 140 miles, right?
Yes, roughly 140 miles.
It took a guy on a really fast horse over a full day of hard riding to cover that. How fast could the Chappe Telegraph send a message across that same distance?
Under good visibility conditions, a single signal could travel from Paris all the way to Lille, passing through over 20 individual relay towers in roughly 2 minutes.
2 minutes. That is just insane.
An entire complex military sentence could be transmitted and fully decoded in under an hour. It was a complete paradigm-shifting leap for humanity.
It really was.
It was the very first time in human history that complex information traveled across a continental landmass significantly faster than any human being could physically travel.
2 minutes. That is essentially real-time communication in 1794.
It felt like magic to them.
I bet. But as amazing as the wooden arms were, the real genius of the Chappe system wasn't just the physical machine itself.
No, it's the protocol.
It was the human beings running it and the incredibly rigorous protocol they were literally forced to follow.
Yes.
Let's talk about the operators, the guys they called the Chappists.
Yeah.
What was their actual daily life like? Because working this machine sounds incredibly intense.
The Chappists were, for all intents and purposes, the living routers of this mechanical internet.
They were human microchips.
They were. They were highly skilled, subjected to strict military-style discipline, and they were required to follow incredibly rigid procedural manuals.
No slacking on the job.
Their workflow was meticulous and genuinely grueling.
Walk me through an actual transmission. A message is coming down the line from Paris heading north to Lille. I am an operator sitting in a tower somewhere, right in the middle of the French countryside. What am I physically doing?
You are sitting in the operating room at the base of your tower. You have 2 large, high-quality brass telescopes mounted securely into the walls.
Okay, 2 telescopes.
One points backward toward Paris, your source. The other points forward toward Lille, your destination. You spend your entire shift staring intensely through the backward-facing telescope at the preceding tower, which might be 8 miles away.
Just staring for hours and hours, waiting for it to move.
Exactly. You just watch the horizon. Suddenly, the tower 8 miles away springs to life. The massive wooden arms shift and lock into a specific geometric configuration.
Okay, I see it move.
You carefully observe that exact shape. You quickly write it down in your official logbook. Then you turn to your complex system of levers and pulleys, and you physically manipulate your own tower's massive wooden arms to perfectly replicate that exact same geometric shape.
So I am literally acting as a human network node.
You are the node.
I am receiving a data packet, reading it, storing it temporarily in my logbook, and then forwarding it to the next node in the network by moving my levers.
That is precisely the function you are performing. But here is where the cognitive load becomes absolutely staggering.
Why? What's the hard part?
The operators on the line were not translating the message. They had absolutely no idea what the message actually said.
Wait, they didn't know?
No, they didn't have the code books. They were just blindly replicating geometric shapes, and they had to do it perfectly every single time.
Wait, think about the immense pressure of that. What happens if I sneeze or I blink or my eye just wanders for a single second because I've been staring through a brass tube for 6 straight hours?
It happens to everyone.
Right. If I misread an angle and replicate the wrong shape on my tower, I corrupt the entire message for the rest of the line. The error could be catastrophic for the Army.
Claude Chappe fully anticipated that exact human vulnerability. He knew that relying purely on human transcription across dozens of nodes without a safety net would inevitably lead to chaos.
So what did he do?
So he engineered a brilliant error-checking protocol directly into the system's core workflow.
How on earth did they error-check a visual signal across an 8-mile gap in the 1790s?
It's so clever. After you replicate the signal on your tower, you don't just relax and wait for the next one from Paris.
You don't just sit down.
No. You immediately shift to your forward-facing telescope and point it at the next tower in the chain, the one you just sent the signal to. You watch them. You wait to see them replicate the signal you just sent.
Wow. So they are visually verifying the transmission down the line.
Visually verifying the packet, yes.
I send the signal, and then I actively watch my neighbor to make sure he got it right. If he forms the wrong shape, I instantly know there's an error on the network.
Exactly. It is a brilliant closed-loop verification system. If you see the next tower display the wrong shape, you immediately send a specific pre-assigned error correction shape on your own tower.
The kill signal.
Right. This forces the next tower to halt, wipe their last logbook entry, and wait for you to retransmit the correct shape.
That is unbelievable to me. It's an analog 18th century version of a TCP acknowledgement packet.
It is the exact same logic.
When your computer downloads a file today, it constantly sends tiny signals back to the server saying, yep, got that packet, send the next one. If a packet gets dropped, it explicitly asks for a retransmission. The Chappists were doing the exact same logical operation with wooden arms and brass telescopes.
The parallels are exact. They really are. This systemic protocol, the standardized shapes, the strict administrative rigidity, the built-in error-checking loops is what elevated the Chappe telegraph from a simple semaphore novelty to a true, robust communications network.
It wasn't just a toy.
No, it laid the conceptual groundwork for how we manage data integrity today.
It is absolute genius. But as brilliant as the error checking was, my earlier point about the sneezing operator really tees up the fatal flaw of this entire mechanical internet.
The environment.
Exactly. Because no matter how perfect your human operators are, and no matter how well-oiled your brass pulleys are, the Chappe telegraph was entirely at the mercy of the physical world. And that physical world was an absolute tyrant.
The tyranny of the environment is the ultimate bottleneck of all early optical networks. As we established earlier, the absolute primary constraint of any visual system is line of sight.
You have to be able to see it.
The signal can physically only go as far as the horizon, and it can only go in a perfectly straight line.
Which creates a massive grinding infrastructure problem. If you want to connect Paris to, say, the southern coast of France, you can't just build one really tall tower in Paris and one really tall tower in Marseille.
No, the Earth gets in the way.
Because of the curvature of the Earth, you literally have to build a tower every 6 to 10 miles forever across the entire country.
The capital expenditure required by the government to build and maintain that physical footprint was astronomical.
I can't even imagine the cost.
You had to survey the land to find the exact high points that maintained perfect line of sight. You had to buy that land, construct sturdy stone towers, build complex wooden mechanisms that could withstand gale force winds without snapping, and then you had to employ, house, and pay highly trained operators at every single node 24 hours a day.
It's basically the 18th century equivalent of laying fiber optic cable across the ocean, but incredibly labor-intensive.
Very labor-intensive.
And here's the kicker. Even if you had infinite money from the French Republic and you successfully built a flawless, sprawling network of towers, you still could not control the atmosphere.
Mother Nature always wins.
The environment was the ultimate dictator of network uptime.
The system was utterly and hopelessly dependent on atmospheric clarity. A little bit of summer haze, heavy rain, snowstorms, and most devastatingly fog could completely sever the connection.
Think about what that actually means for the user experience back then.
It's incredibly frustrating.
A thick fog rolling in over the French countryside wasn't just an inconvenience. It was the 18th century equivalent of a massive nationwide server outage.
The whole grid just dropped.
Your internet literally goes down because it's cloudy outside. You have an urgent life-or-death military order from Paris. Enemies are massing on the border, and the message is just stuck in a tower in the middle of a vineyard because it started to rain.
And of course, the most predictable, inescapable environmental failure of all was nightfall.
Right, the sun goes down.
The original Chappe telegraphs were virtually useless at night. They did try experimenting with attaching lanterns to the ends of the wooden arms.
Oh, that sounds like a fire hazard.
It was incredibly dangerous. The lamps would constantly blow out in the wind, and the glaring light often distorted the geometric shapes so badly they couldn't be read. For all intents and purposes, when the sun went down, the entire French communications network went completely offline.
Which is terrifying if you are actively fighting a war. The enemy doesn't stop marching just because the sun went down and the network is down.
No, they take advantage of it.
But beyond the weather, there were massive operational constraints too, like the bandwidth limitation. Even at its absolute fastest, the Chappe telegraph was still a very low bandwidth medium.
The friction of encoding and decoding was immensely high. As we said, the operators on the line didn't know the code, but the director of telegraphs at the start and end points did.
The guy with the big book.
Yes, the director had a massive, highly classified 92-page codebook. Each page in that book had exactly 92 lines of text.
So they weren't spelling things out letter by letter like Polybius did with his torches?
No, that would be far too slow.
They were literally sending coordinates for the codebook itself.
Correct. The first signal on the tower would indicate the page number. The second signal would indicate the specific line number on that page.
Oh, that's smart.
It was a brilliantly compressed system, but it still required a human to manually flip through heavy books, write down translations, and format the final message. Because of this high friction, messages had to be highly compressed, bureaucratic, and absolutely vital.
No casual chatting.
None. You couldn't just casually chat over the optical telegraph. The network was reserved strictly and exclusively for vital state business.
And there was one final glaring vulnerability with broadcasting a visual signal across the entire countryside. Security.
Security is always the issue. The inherent flaw of any optical network is that it broadcasts its data completely out into the public visual spectrum.
Anyone can see it.
Anyone with a spyglass, a line of sight to a tower, and basic deductive reasoning could intercept the transmission.
It is literally the ultimate unencrypted public Wi-Fi network. You are just shouting the data into the sky for anyone to read.
Which meant that governments were forced to rely entirely on cryptography to secure their communications. They physically couldn't hide the transmission itself because it was a giant wooden arm on a hill, so they had to hide the meaning of the transmission while it was sitting right there in plain sight.
Security through encryption, not obscurity.
Exactly. This is why the code books were kept under such strict lock and key. Even if a British spy sat on a hill in France and perfectly recorded the arms forming a 7 and a 4, they would have absolutely no idea that 74 meant divert the artillery to the left flank without possessing the highly classified cipher.
So, to summarize the reality of this system, you have a network that is insanely expensive to build.
Very expensive.
It requires humans to sit in cold stone towers staring through telescopes all day. It completely crashes every time it rains or gets dark. And it can be intercepted by literally anyone standing on a hill with a magnifying glass.
It sounds chaotic, brittle, and deeply flawed by modern standards, I know. But this is exactly where we need to connect the struggles of the past to the infrastructure of the present.
Why is that?
Because despite all of these massive physical flaws, the architectural concepts forged by the Chappe telegraph and all the other optical networks did not die when the fog rolled in.
The ideas survive.
They did not disappear when the electrical telegraph eventually rendered them completely obsolete. They became the invisible, enduring scaffolding for every single electronic network that followed.
The structural legacy is really what truly matters here. When we look back at the source material, what is the actual lasting impact of these optical networks? What is the invisible blueprint they left behind?
There are 4 major legacies.
Because there are 4 major legacies that we really need to unpack to truly understand how we got from giant wooden arms to the modern internet.
The first and arguably the most profound legacy is the establishment of the principle of relays.
Relays.
Yes. For thousands of years, as we discussed, the message was permanently tied to the messenger. A runner or a pigeon made the entire exhaustive journey from start to finish.
The data and the carrier were one.
The Chappe telegraph shattered that paradigm completely by breaking the journey into discrete, manageable, repeating hops.
It proved that information is fundamentally independent of its carrier. You can take a thought, abstract it into a visual symbol, pass it across an 8-mile gap, receive it, regenerate it perfectly, and then pass it again.
It flows.
The information flows like water through a pipe, while the nodes, the towers, stay completely stationary.
That relay concept is the very beating heart of modern digital routing. When you send an email or a text message today, that tiny data packet doesn't travel in a straight, unbroken line to your friend's phone.
No, it bounces all over.
It bounces through dozens of different routers, servers, and switches across the globe. It is received, read, and regenerated at each step, exactly like a visual signal bouncing through dozens of Chappe towers. The underlying architecture is identical. Only the medium has changed.
That is just mind-blowing when you really stop and think about it. We're just using much, much faster routers now.
That's all it is.
Okay, legacy number 2, developing standardized codes.
The optical era fundamentally forced humanity to realize that complex human thought and language had to be systematically reduced to a standardized set of abstract symbols if it was going to be transmitted efficiently.
You can't just send raw language.
No. Whether that was the 5x5 grid of Polybius torches, the specific arrangement of colored naval flags on a mast, or the geometric angles of the Chappe regulator arms, they were all doing the exact same conceptual thing.
They were essentially digitizing language before digital technology even existed.
Exactly. They were creating the direct conceptual ancestors of ASCII or modern binary code. Today, our computers agree that a specific sequence of electrical pulses, ones and zeros, represents the letter A.
It's just an agreement.
In 1794, the French agreed that a specific angle of a massive wooden arm represented a specific line in a codebook. The protocol of deep standardization was born entirely out of the necessity of the optical signal.
Legacy number 3 is all about the grid itself, right? Highlighting the importance of physical infrastructure.
Yes. These optical systems, particularly the Chappe towers, proved that robust, reliable communication at scale requires dedicated, permanent, and expensive physical architecture.
You can't just wing it.
You cannot rely on ad hoc solutions or natural features anymore. You have to actively build the grid.
You have to essentially engineer the environment itself to support the network. You have to build the towers on the high ground, cut down the trees in the way.
And that strategic placement of Semaphore towers maps perfectly to how we build networks today. The logic of finding the absolute highest point of elevation for a Chappe tower in 1794 is the exact same logic used by telecom companies today when they decide where to build a 5G cell tower or a microwave relay station.
They need the height.
They are still hunting for the perfect line of sight, just in a completely different invisible spectrum of light.
And finally, legacy number 4, demonstrating the absolute value of speed and efficiency.
Once human society actually experienced the intoxicating ability to send a complex message across an entire country in hours instead of weeks, there was simply no putting the genie back in the bottle.
They were hooked on speed.
The optical telegraph fundamentally altered our expectations as a species. It proved the immense geopolitical and economic value of sheer speed.
Basically created this insatiable demand that it couldn't fully satisfy itself, mostly because of the weather and the nightfall.
It left us wanting more.
It proved that fast communication was vital, which directly motivated and funded the mad scramble for the next technological leap. Without the Chappe telegraph proving the core concept first, the electrical telegraph might have taken decades longer to secure the necessary funding.
Exactly. It forced the evolution of the species. So when we synthesize this entire historical journey, we see a profound, almost beautiful continuity.
Let me try to pull this all together for a second.
Go for it.
When we look at a modern fiber optic cable today, which is the literal backbone of the global internet, we tend to look at it as this modern miracle of advanced physics. It feels like pure magic.
It does feel like magic.
But really, if you break it down to its absolute conceptual core, we're just looking at a microscopic, hyper-fast version of Claude Chappe's wooden towers.
How do you mean?
Well, think about it. A fiber optic cable is just a very long glass tube transmitting tiny rapid pulses of light. We are still just blinking lights at each other to pass messages down a long line, node to node, relay to relay, just exactly like they did with torches and wooden arms.
True.
The only real difference is that we got so tired of the fog shutting our national network down. So we took the light, we shrank it down to a laser, and we trapped it inside a sealed glass tube buried in the ground so the rain can't ever touch it. But the fundamental logic, passing a signal via light across a physical distance using relays, that literally hasn't changed in 200 years.
That is a beautiful synthesis. The underlying logic remains completely untouched. Only the medium, the friction, and the sheer velocity have evolved over time. The intense human desire to connect, to warn each other, to coordinate our complex societies, that desire forged these logistical pathways long before electricity was ever even harnessed.
The desire came first.
The Chappists and their freezing cold stone towers fought the physical environment every day to establish the very concept of the network relay. And we are quite literally still running our digital lives on the conceptual rails that they laid down.
It is genuinely incredible to trace that lineage backwards. We started this deep dive mired in the heavy physical limitations of talking drums and running human messengers, where human thought was stubbornly trapped by physical mass.
Stuck on the ground.
We saw humanity desperately look to the sky, using Native American smoke packets and Greek torch grids to try and break that physical bond with the Earth. We watched the system scale up massively with naval flags in the open ocean to create a macro vocabulary.
A huge leap.
And finally, we reached the mechanical pinnacle with the French Telegraph arms, passing visual data packets across an entire continent in mere minutes. These slow, weather-dependent, highly vulnerable optical systems literally invented the concept of the network relay and the communication protocol as we know it.
They proved definitively that human ingenuity can take a complex thought, abstract it into a visual signal, and push that signal across seemingly impossible distances. They conquered geography.
So the next time you pull out your phone and you instantly text a friend on the other side of the globe, take a single second to appreciate the deep architecture behind it. Your message is rapidly jumping from node to node, routing itself intelligently around obstacles, and it is guided by the exact same structural logic established by a freezing guy staring through a brass telescope on a wooden tower in 1794.
It is a profound continuity of human effort. And looking back at this era leads me to a final thought, drawing on a subtle but vital theme from our sources that we haven't deeply explored yet, regarding a shift in the very nature of information itself.
Oh, what kind of shift?
The historical record explicitly notes that as communication got faster, especially as we transitioned out of the optical era and began the electrical era, it created an entirely new culture of deep anxiety.
Anxiety. Just because the news was arriving faster.
Because the expectation of news completely changed. It demanded what historians often call a journalism of immediacy.
Oh, I see.
In the era of the horse, you didn't expect news today, so you didn't worry if it didn't arrive, you just waited. But the Chappe Telegraph introduced the expectation of real-time updates for the first time. Suddenly, a lack of signal didn't just mean no news today. It meant a catastrophic system failure. It meant something was horribly wrong.
Right. Suddenly, waiting became unacceptable. The silence became deafening.
Exactly. The Chappe Telegraph began a massive, permanent psychological shift in human society. We began moving away from focusing heavily on the content of a message, like a deeply considered, handwritten book or a long letter carried by a slow messenger, and we started focusing obsessively on the connection itself and the sheer speed of the message.
It became all about the speed.
The medium began to overshadow the message. So, here's something for you to mull over as we wrap up today. Today, our digital networks are practically instantaneous and functionally flawless compared to a wooden tower caught in a fog storm. But by completely eliminating the friction of distance and time that those early optical operators fought so hard to overcome, have we prioritized the speed of our connections over the actual depth of what we are connecting to share?
Oh, wow. That is a heavy, heavy question to leave on. The idea that by perfecting the speed of the message, we might have inadvertently degraded the actual weight of it. We started this deep dive asking you to imagine sending a message without wires or electricity. It turns out, figuring out how to send it across the continent was only the first part of the puzzle. Figuring out what that instant speed actually does to us psychologically is the puzzle we are still trying to solve today. Thanks for joining us on this deep dive. Keep questioning the grid, and we'll see you next time.